there's no magic Wizard of Oz behind the curtain. You know, it's just, that's how every place works. You figured out. Some places are different than others, but in that year especially, everyone was scrambling to figure it out. And so one of the labs we went mostly computer, which is nice. This really nice thing about our field is, compared to some other sciences, we have a very portable art because we're digitized now. It's really amazing. We don't realize it. You know, you could go do, you know, you have a laptop, you could do science and do engineering, which is cool. Other fields have, you know, all these time issues and material issues that had to stop for COVID, and we, you know, DMC went home, did like Simulink labs, did MATLAB labs, and that's DMC is honestly, most of the time in DMC lab is computer based and based on a few physical experiments. Have you been through yet?
No, I'm taking it next semester.
Okay, cool. And so that one went home, became a computer lab, easily already was, but measurements, you know, I didn't know what to do, so we did breadboards at home. We had little pocket oscopes. There's a whole, that's right there. There back in that cabinet is function generators, oscilloscopes, power supplies, and that was measurements at home. Yeah, I can show you. I was going to try to.
Do you think that like mechanical engineering is a pretty good spot right now, just with like the big projects that are happening, and also like you said, like we don't need like a dedicated lab to do a lot of this stuff that we have to we can work on. We could all do it on either a computer, like even like in CAD or in MATLAB Simulink. So
yeah, it's a flexible space, and you as a student, you won't necessarily have a permanent lab or yet for a little bit of time, and so you can get a lot done at home. You can get a lot done on your mobile workstation, your laptop, and it because you have a lot of tools, you know, software-based tools. I say you could do that anywhere, but it would be hard to do it without the software that you have access to. Sometimes I think about what it would take to do my own designs without the university, and at minimum I'd have to have a software package, you know.
Yeah.
And so we get a lot of the resources here.
Yeah. So one thing I wanted to talk to you about was the robot project that you were working on with the was it Y12 or was it another nuclear?
Well, we're on several different robot projects. I think the closest that I've gotten to Y12 is we work with some students. We have a PhD cohort that are Oak Ridge National Labs students. So maybe we're thinking about a different project. The project that you're referring to is probably the TVA power plant project. So that project is titled the TVA ice condenser, is for short, and its a long name would be thermal treatment of power plants. And that's not the official name, but thermal treatment in nuclear power plants, and it's a TVA related or TVA funded project we're working on in the mechanical engineering department. Yeah, I'll just stay closer and talk louder. I guess I have a low voice, kind of mumble.
I mean, I don't know if you know Lex Friedman, but he gets that criticism all the time. He just mumbles.
Who's that?
He was a researcher for MIT's like robotics and all autonomous vehicles, but now he has a podcast, and he's like this like Russian professor guy, so he just has like a very like monotone voice that's like kind of low, and people complain about it, but I mean he has a lot of good ideas and good guests on, so it kind of balances it out. There's a reason why people listen to him, so it's not like the main like, it's not that big of a detriment.
I was actually listening to a YouTube with a guy talking about actually the nuclear robots in Fukushima. Fukushima nuclear robots. This guy's YouTube was I don't remember what it was, but he was super dry. I mean, he sounded like robot voice, and he was just spitting out the information. But he was getting views, so that's one approach, just to get the information out.
Yeah.
But he wasn't doing an interview. He was doing like a voiceover, just like a overview of a topic. He did like the last 20 years in nuclear rope, because Fukushima, the disaster happened not 20 years ago, but 15 years ago almost.
Was it 2007 or 8?
Yeah, so, I mean, if you're just trying to get the information across, adding a lot of bells and whistles doesn't necessarily help. I mean,
no.
And so in class, I go back and forth. We add a little bit of story, but then I kind of realize the students aren't there to hear me tell stories and talk about myself, and we kind of want to get the material across. So there's a balance, I think.
Yeah,
everywhere.
I mean, it kind of helps the more personal side, because people get like they say more invested than just reading from a lecture the entire time. It kind of, I don't know. There's like a big lull in like you have on Monday, so it's only like 50 minutes. But if it's like the 120-minute class where it just drags on, it kind of needs some like re-engagement,
yeah, I mean, even 50 minutes of listening to someone talk is probably too long. I think there's research that shows that you can pay attention for so many minutes. 50 minutes is past that number. So we try to, I mean, that's one of the things I'm trying to do in measurements is do those activities. They're not great. They need development, but I know it helps the morale to break the lecture in half. And it's clear that it makes the time flow faster, obviously, and less, drag, I guess.
Yeah, I wanted to talk to you about the robot with the nuclear waste.
Yeah, so the project we're working on is we're working on a project, a TVA funded project, and we're developing a tool for a thermal treatment in the nuclear plant, and that's an ongoing research project here at Tennessee Tech. So I can share some details, but I can't say everything.
No, that's all right. I just talked to do you know Elijah Barrett? He's in machine design, but he works for Y12 too. So you could talk about a few things, but obviously there's a lot of red tape there.
From the big picture, what we're doing is building a tool to go into a hard to reach place and perform a thermal treatment. So it's actually a de-icing job in the plant. And so right now we're working on the set of tools to do that, set of procedures, and we're in the prototyping and testing stage right now. The primary part of the tool is is a robot arm. It's a remote deployed robot arm that has this de-icing tool mounted on the end. So I mean, you've probably seen and heard of a lot of different robot arms, and the kind of the different type of application than maybe a traditional manufacturing environment that we see robot arms in.
Yeah. So what are some of the challenges of like the robot arm and the application that you're trying to design it for?
Well, there are several different challenges in this problem because it's a complex problem. From my side, the engineering challenges that I've been dealing with the most are we could divide them into kind of mechanics challenges, mechanical challenges, and then software. I would probably say software, and then electronics. So I really want to describe them. I could split them into 3 areas. And there are robot arms available. So mechanically, just building a robot arm is not an unsolved problem, but the environment we're working on is a confined space. So mechanically, the large challenge is building this robot arm small enough to fit into the operating environment. And there's actually a kind of a way to enter through a small hole and then get into the environment and then do the work. And so that entrance condition is created some constraints on the mechanical design. So that's been one of the large challenges. This thing has to be small to sum that up. And so that makes the design more critical. And it's a robot, so there's a set of computers running inside. So the electronics design has brought challenges. Similarly, space-based challenges. I'm kind of asking to do a lot in a small space, computing-wise. So actually, I've got one version of it right here. It's not a very pretty version of it, but trying to fit all the electronics into a small space is one of the kind of coupled challenges between mechanical and electronics, and then bringing all that together with software is kind of what can be a daunting task. We have to do couple all this together, and so I guess the third main challenge is probably the software integration of the system, because there's kind of a lot going on there.
Yeah, I was curious because I'm not really that familiar with the robotics side of mechanical engineering. It's more of what I see as like a EE and CS problem combined with a mechanical problem. So there's a lot of integrated systems that you have to have a lot of background knowledge in. Like, how did you get involved in robotics in the past?
Well, yeah, I'm glad you asked, and it's really interesting you say that, because robotics is an integrated field, but it's very much a mechanical engineering field, because it is a physical machine. It is a mechanism. It's a beam. It has to be designed so it doesn't break and hold load. So even though it may seem like an electrical engineering field, it's definitely integrated. But on the other side, we need the robot needs electronics, and the robot needs software. So how I got involved in robotics, I've always knew I wanted to do engineering, and I've been working on mechanical systems casually for a long time, and actually, my father pushed me to look into robotics, kind of around high school. So I started working on like a Lego Mindstorms project in high school, and that kind of slowly developed into where I am now. So I actually toured the robotics lab over there in Clement Hall here at Tennessee Tech when I was when I was looking for colleges, and there was some interest there, and so I came to Tennessee Tech for mechanical engineering, but I still wasn't decided. You have a lot of different directions you could go. You see it your first year, but so at some point in my first or second year, I was sitting on the dorms over there, dorm steps. Marshall is not quite there anymore, but a RA came up to me and said, "Hey, do you want to come to the robotics club meeting?" And so I kid you not, I got off the steps of the dorms and walked over to the engineering quad and met some electrical engineers, and mechanical engineers, a group of students that had just put together the robotics club. And so I kind of helped me continue my interest in robotics that I started previously. And we worked on some projects. We went to a couple of robotics competitions, and we're actually going back to that robotics competition this spring with the Autonomous Robotics Club, actually. So to come full circle, that was over almost 15 years ago.
Oh, wow.
And so I'm pretty happy to say that the club is still alive and active, And so again, we'll be going back to IGBC. So there's my little story about how I got into robotics. And to summarize, you can't do it with just mechanical systems.
Yeah.
And so that's I guess that's how I got here.
Well, some robots you can power them like hydraulically, and then we realized that having like electro servos and motors can be a little easier to control and easier. Or is there?
Well, yeah, I mean, some machines are still powered with hydraulic systems. Robotics, not terribly common, but because fine control of hydraulic systems is tricky,
okay.
Right?
Yeah.
So to do well, one of the common or universal problems that needs to be solved for a robot to do something is position control.
Mm-hmm.
If either an arm needs to move the tool to a certain place, or a robot vehicle needs to drive to a certain place, this typically requires fine position control of your outputs, your actuators, and this can be done with hydraulic systems, but is much easier and now more cost effective with electronic motors and computer feedback, computer control.
How sophisticated are modern robot arms, like the ones like in manufacturing and the most like industry grade compared to, say, the early ones? Like, are they more durable and or like at a similar scale to like CPU development, or are they still like in the early development?
Well, robot manipulators or robot arms have matured, are a mature technology. Okay. So I mean, so in the really in the 80s, traditional, what we could call traditional robotic manufacturing, involved using large-scale robot arms, typically a 6 degree of freedom robot arm. You may have seen them in a picture of a automotive factory, doing welding jobs or other repetitive jobs. That type of technology is very mature and effective at automating certain types of manufacturing tasks. Those types of tasks are typically large production, large part volume, and not terribly flexible environments. So places like assembly lines and other large-scale production jobs, and those that arm technology is still developing every day, but is somewhat reached a fairly optimal point. But there is a kind of a new type of arm that is developed out of the need that type of technology doesn't provide. And for instance, those large-scale robot arms must operate in an environment without humans. Mm-hmm, So while that technology is successful, it is rigid in that sense. So there's a kind of a new robot arm that's developed out of that called the Cobot, which is collaborative robot. And so the real one of the new technologies that we're seeing is really the safety features that allow a robot arm to exist and work with a human in a local space. So the robot arms I mentioned that have been used since the 80s, you would never be in proximity with while it was turned on. And but now there is a demand for a more flexible automotive manufacturer, a more flexible automated manufacturing ability. For instance, not every company has the ability to build an assembly line around their next product, and so this ability for a more flexible robotic work cell will allow for smaller companies to utilize the benefits of automation. So there are some new robot arm technologies, and mostly they are in that cobot safety area.
Okay, yeah. So does that mean it has like sensors to detect like human?
That's part of it. Part of it is the sensing has come a long way, but it's a little more than that. Compared to a traditional system, you could use a sensor to sense whether a human is in the field or not, in the area or not, and then immediately turn the system off if the human entered. That's not the type of safety feature I'm talking about. This modern system would actually allow the robot to continue to operate with the human in that space through some extra sensors. There's more sensors in the robot arm, more sensing at each joint. And one way that can be handled is through modeling and through a feedback control system that predicts how much power is required to do a certain job.
Yeah.
For instance, if the robot was required to hold this microphone here, I could model the statics that say we need to apply this much load to hold this here, and if those loads are sensed to be different, the robot will detect that as a contact with an unknown environment. So a little bit more smarts and sensing are the primary way these safety features are being added. And in general, things are getting a little smaller.
Yeah.
So the cobot is not necessarily a direct replacement for the large robot arm that we're talking about, but also a modified robot arm that would work in a different space. So the third part of that safety feature was just bring the scale down a little bit, and move a little slower.
Okay, so it would have less power than, but in the scale, if it's going to be a smaller arm, then it should have
less power, and that kind of comes with moving slower.
Yeah.
So you can do your dynamics there, and also the right amount of power.
Yeah.
So if you think about, again, if it's actually modeling the job it's doing, less wasted power.
Yeah.
And more efficiency, and that could reduce the chance of some damaging impact.
Yeah.
If you would carefully move something.
Right? Yeah. Fine motor control is something that is hard and it's something with the biggest motor that you could throw into it, like a industrial application. So it would make sense that a smaller, more human-friendly robot would also be more efficient and have. Well, I'd imagine that the robot, since you said like it's not going to be in a dedicated assembly line, then it would be able to be programmed on the fly with you would have to have like a technician to be able to say we want it to do something else, so we can easily change its function. Yeah,
that's definitely the goal. And so if you go back to kind of the a base definition of robot, you usually hear that word reprogrammable.
Yeah.
So it's not just a machine that can make a very special part.
Yeah.
It's a machine that can make a general set of parts is reprogrammable. And this the ideal cobot would be reprogrammable by a skilled technician, and not require an engineer or roboticist to do that reprogramming. And now a traditional robot arm can do that, but that reprogrammability is limited.
Okay.
And so there definitely is lots of research in the area of custom automated jobs, and for small batch jobs that are we might do 100 or 1,000 or a dozen parts, and then next week want to do a different set of parts.
Yeah.
And the cobot serves a role there in terms of manufacturing flexibility.
Yeah, that makes sense, because the original robots we talked about, they're for the big companies that just want to pump out hundreds of thousands of this specific part, and they'll probably do that until it either wears out, the robot, or the the need for it won't be there anymore. But the new robots, they should be able to be a little more general, and they should basically do a lot more than just one job compared to the original one.
Yeah.
This will help smaller companies that have less scale, right?
Right. I think what you said is exactly true. Smaller companies don't have the ability or the scale to build an assembly line.
Yeah.
But to be competitive, still need to benefit from automation, or can benefit from automation if we can make it available at the smaller scale.
Yeah. So is a 3D printer considered a robot?
Oh, okay. So I think so. Well, depending on the way you look at the definition, it is a gantry robot. So if you look at it from our Intro to Robotics definition of a robotic manipulator, it is a gantry robot. It controls XYZ position.
Yeah.
It in some ways is reprogrammable in that I can send it different parts.
Yeah.
But in some ways it does the same job every time, and then it just prints the part I send it. So, yes and no. That just shows that word gets used in a lot of different ways.
Yeah. Sometimes misplaced. I mean, it's definitely a neat piece of technology, but yeah, I was talking to a grad student about the scalability of 3D printers, and will they ever consider using a 3D printer over, say, stamping or forging a part, or is it just too slow to ever?
Oh, so in scalability, you mean part volume?
Yeah,
not part size.
Like past prototyping, like
not part size, right? Yeah. Okay. So I think that again for relatively small jobs, but possibly still production, they are being used now.
Really?
But it's still a rapid prototyping technology.
Yeah.
And especially this type of FDM printer, this is a prototyping machine. It's designed for making parts to test in the lab, or we make functional prototypes, but it's definitely FDM was not developed as a production technology.
Yeah.
And injection molding is more cost effective at large scale than FDM.
Yeah.
And I don't know where that transition is, but always will be past a certain level. But there's certain things you can do with certain technologies in 3D printing that are not available in those traditional manufacturing technologies. So, but things are changing, and because again, I think printers are used in production in smaller scale.
Now, I'm wondering what if they're using more advanced parts than PLA because of the material property.
Yeah, PLA is a good beginner material because it's forgiving in terms of settings, but it's not terribly desirable in its most natural sense. Yeah. There's some modified PLAs that perform a little better. Yeah. Our mechanical engineering fabrication lab is using a modified PLA for general purpose parts, mostly because the users, a lot of the users are new to 3D printing.
Yeah.
And it's forgiving on the bed surface. But this, I've been printing out of PETG. It's a little tougher than PLA. It has similar strength, but it's a little tougher. And but it's not. It has limitations.
Yeah.
And benefits.
What do you think about other materials like carbon fiber 3D printing? Like I was talking to Bryson. I didn't even know that he it was able to 3D print any material other than like a plastic. Because isn't carbon fiber more of a advanced strand? It's not like plastic where you can like melt it down and then remake just based on heat, right?
Yeah. Carbon fiber printing is a now available technology. It does course, is pretty high end, and so we're not doing it for general purpose prototyping. But again, here in mechanical engineering, we do have a carbon fiber printing machine downstairs, and in general, it's primarily printing in nylon. So it's a nylon FDM. So it's a machine very similar to this. That nylon is injected off the spool in a controlled manner, and nylon itself has a lot higher strength, maybe 25% maximum or possible strength increase over your other materials. But the carbon fiber is introduced on a second filament and placed in almost in a support structure manner, not support structure, in a internal
like
stiffening structure. And so once again, the carbon fiber printing that we're doing here is primarily nylon printing with a carbon fiber strand that's printed from a second extruder to stiffen or strengthen the overall structure.
Okay.
And theoretically, some of the strength can go way up with those parts, but they, like all high strength composite materials, they tend to have some issues with brittle failures and other things.
Yeah.
The one project that I worked on that we used that is the human powered vehicle competition, something I'm fortunate to have been involved in for years. It's been a few years since we've been into a race, and hopefully we'll get to go back soon. But we've been working on printing, some of the preliminary engineering work on making a carbon fiber frame, and they've been using that nylon carbon fiber combination print to make couplers.
Okay.
For that bicycle or vehicle project.
All right. Yeah. That makes more sense than just printing carbon fiber straight into a prototype part. It doesn't seem conducive to 3D printing.
Yeah,
plastic.
I think for one it would be too brittle. I think just pure carbon fiber from FDM would be brittle, and also is expensive.
Oh yeah.
So even the nylon with some carbon fiber in it, the price tag goes up on materials quite a bit, and so a pure carbon fiber is probably cost preventative, especially for our prototyping and experimenting stuff.
All right. Yeah, I definitely wanted to ask you about 3D printing because since you actually have one and you've done a lot more than I have.
Yeah, I've done quite a lot for my needs, for prototyping needs. It is interesting because 10 years ago I was making brackets on a little 3-axis mill, and we still do that when needed, but sometimes it's a little faster to make a bracket. Get your printer to make a bracket. One of the other exciting things is I've got parts waiting to go on our Mark Forge metal printer. So actually also here in the mechanical engineering department, or it's housed in the college, but it's here with us in the building. We have this direct laser sintering printer, metal laser sintering printer, and we spent about a year getting that system set up and tested, and I'm actually fortunate to be getting some parts run through there this coming season. And that material, we're able to do stainless steel or aluminum, different metals, allows me to bring that strength up tenfold from what I can do with my plastic here. So, and I have a few parts on the robot we're making actually that are have some critical areas that need that high strength for reliability, and so we are really fortunate to be in the age when I can't just print plastic. I can print carbon fiber or stainless steel if I need to.
Yeah, that's pretty cool. I never thought that they would be able to. You see like the old like blacksmith, the way that they have to go through all the taking out the carbon and like smashing it into make it into the material. Well,